Okay, this is part 3. In the first video I said there's only 2 parts. I lied, there are 3 parts. This video is solving more complicated log equations and then checking for extraneous roots. We checked our previous examples to make sure our solutions were valid. In that if you plug them in for x, you actually came up with the value on the other side. So we're going to check these ones as well. Mainly checking to make sure that they don't give us a negative inside the argument for a logarithm, because the input to a logarithm needs to be positive. So for example, if we got, say, -1 as an answer to this first equation, it would be invalid and rejected as a solution because it would create a negative argument inside this log function, which wouldn't be in the domain of any logarithm with any base. So we'll check the validity after we evaluate. So let's do a couple examples here, and then there's one for you to try at the bottom after. The first one here is the log of 3x plus 1 base 4 equal to 2. When you have a logarithm equal to a single value, the easiest way to evaluate this is to solve this, is to rewrite it as a power, using 2 as the exponent and 4 as the base, and this argument as the answer. So if we rewrite this as a power, we would just have 4 to the exponent 2 equal to 3x plus 1. And now it's actually a pretty easy linear equation to solve. 4 to the exponent 2 is 16. 3x plus 1. Subtract 1 from both sides, we get 15 equals 3x. And divide both sides by 3, we get x equals 5. If we plug x equals 5 back into our original, we get 3 times 5, which is 15, plus 1 is 16. 4 to the exponent 2 is 16, so we actually have a valid answer here. We don't get a negative argument when we plug in 5. The argument becomes 16, which is valid because it's positive. So we have a good solution here. For B, a little bit more complicated here. We can apply the same strategy, rewriting this as a power, but it might be easier to clean it up first before we do that. So let's get rid of this radical. How do we get rid of a radical? Well, we use the law of logs for roots. And if we have the 5th root, we can rewrite this as 1 over 5 times the log of x squared minus 21x. Spoiler, this is going to be a quadratic. We actually have a quadratic argument here. So if we divide both sides by a 5th, we get 10 over 5 on the right side, and the log of x squared minus 21x on the left side. 10 divided by 5 is 2. And we've got the log of x squared minus 21x. And now we can rewrite this as a power. The base is 10, so we'd have 10 to the exponent 2 equals x squared minus 21x. So 10 to the exponent 2 equals x squared minus 21x. And I'm going to work down here, this column here, and kind of invade the space of C. Let's see. 10 to the exponent 2 is 100, and if we subtract 100 on both sides, we can isolate our quadratic here on the right side. So that would be -100. And now we have a quadratic that we can try to factor, looking for numbers that multiply to -100 and add to -21. We can come up with the numbers -25, and 4. So we get x minus 25 and x plus 4. And there we have a factored quadratic. So to solve, our solutions would come from each factor. X is 25 and x is -4. And now we have to check to make sure both of these solutions are valid by plugging them into the original equation and making sure that the argument, or what will go into the log, comes out as a positive value. If we plug a positive 25 in, 25 squared is a large positive number. Subtract 21 times 25. 25 squared is bigger, so we'll get a positive here. So 25 is good. If we plug in -4, -4 squared is 16 times -21 times -4 will give you a positive. 2 positives added together give you a positive, so -4 is okay as well. Quick recap here. What did I just do? I plugged in these two answers into our logarithms argument to make sure that we're going to get a positive value here. You can do the math to support it, or you can do a quick check in your head by plugging those numbers in and hoping that they come out positive. If they don't, just don't box your answer and say that this is not admissible or it's an extraneous root, so it would not count. You could designate that by not boxing it and writing the word extraneous, or not a solution, or something that indicates that it's not one of the solutions to the equation. Okay, one last example here. We have the log of 2x plus 2 base 8 minus the log of x minus 1 base 8 equal to the log of x minus 5 base 8. So what are we doing here? Well, we can use some log laws to simplify. And to do that, we have subtraction here, two logs with the same base, so that turns into a division statement. So that would be the log of 8 of 2x plus 2 over x minus 1. And on our right side, we have the log of x minus 5 base 8. When you have two terms on either side of an equal sign that have the same base, just like when you have powers with the same base, you can rewrite it as a equation of just the arguments. So we could rewrite this as 2x plus 2 over x minus 1 equal to x minus 5. The reason we can do that is if we were to turn each side into a power with a base of 8, so 8 to the exponent log of 2x plus 2 divided by x minus 1 base 8 equal to 8 to the exponent log of x minus 5 base 8. The bases are the same in the power and the log, which undoes both and leaves us just with the argument. So we have 2x plus 2 over x minus 1 and x minus 5. And now we have a rational equal to a linear function. The way we can solve a rational equation is by multiplying both sides by the denominator. So on our left side, that would leave us with just 2x plus 2. And on our right side, it would leave us with x minus 5 times x minus 1, which if we expand, gives us x squared minus 6x plus 5. And now if we collect like terms, on the right side, we'll get 0 equals x squared minus 8x plus 3. And this is a quadratic that we can look to factor. Terms that multiply to 3 and add to negative 8. Oh, we can't factor it. So we'll need to use the quadratic formula to come up with our roots. In the interest of time, I'm just going to say use quad formula. And if we use the quadratic formula, we get two answers. X equals 7.6 and x equals 0.39. So now we need to check to make sure both of these answers are valid, and we do that by plugging them into all three of our log terms here. Any term that has an x, we need to plug in our root and make sure that the root gives us a positive argument. So if we plug in 7.6, 7.6 times 2 plus 2 is a positive number, 7.6 minus 1 is a positive, and 7.6 minus 5 gives us a positive. So 7.6 is a valid solution. Let's try 0.39. 0.39 times 2 plus 2 gives us a positive. 0.39 minus 1 gives us a negative, as well as 0.39 minus 5. So 0.39 is an extraneous root. So therefore, the only answer to this quadratic log equation is just 7.6. That's the only solution. That would be the only x-intercept if we graphed. Well, I guess it wouldn't give you an x-intercept because we don't have it equal to 0. So this would be the only place that this graph would cross this graph. just one time. Okay, and there's a practice for you to try. Make sure you check your answers for extraneous roots, and then you can view the solutions on the Moodle.